absolutely. It's sort of a cross-section of the research I've been doing and where I'm moving from there, emphasizing DE and Jesse cars, as Quentin pointed out yesterday. Transition metals in nature, I changed it a little bit because I feel that there's a little bit more discussion needed about community building, and so I have a larger segment and some ideas how to do that. So transition metals in nature, most of you know me for several years, and where I'm coming from, deep earth, high pressure, computational mineral physics. But here's the objectives really, and we have talked about a lot of these yesterday. It's a laundry list more than everything else. Materials behavior at high pressures, high temperatures. What do they do? How do they differ from ambient condition materials or materials at ambient conditions? Complex materials, multi-phase, obviously, solid solutions, strongly correlated mud insulators, for example. Dane has been talking about that a little bit yesterday, and maybe Matteo is talking about that a little bit later. Thermal properties, JJ is going to talk about that. Obviously, there are lots of things that we would like to know. Thermoelasticity, Renata has mentioned. And so all of that goes together with efficiency. The calculations have to be done in a timely fashion. And so over the last maybe 2 years or so, we have been looking at iron-bearing Wärtsilite. So why does Wärtsilite, iron in Wärtsilite, partition in a very particular way? There's 3 octahedral sites. The M2 sites, surprisingly, has been found to be depleted in iron. Why is that? So we used first principle calculations to explore these several possibilities. And one of the solutions that we find is preliminary results, though, but what we find is that the strain energy associated with the different sizes of magnesium and iron probably causes that effect. So it's strain penalty related, and so we're in the process of putting all that together. My student is in the process of putting all that together. Then as time has progressed, we move towards sort of from the Earth deep interior towards the surface, and we have been looking a little bit into environmental problems. This is looking at structural refinements for sulfates in this case, for Superfund sites, for example, and very acidic environments. That's a study together with neutron scattering, X-ray scattering, and figuring out what at least most of these peaks mean here in these neutron scattering trace. It turns out that it was impossible, to the best of our knowledge, to refine the structure. And the reason it turns out from the computations is that you have 2 different structures that are very close in energy, and one of them has the H3O plus groups that are shown here. On this side and on this side. So you have a hybrid structure, which leads to broadening and a difficulty in the neutron and X-ray diffraction refinements. So we're helping along here really to do some hypothesis testing and to refine some of these structures. Then I went on sabbatical last year, I guess, yep. And that's when I decided to go in Department of Chemical Engineering. And we started thinking about science and society and energy production for the future. And here's one plot just to emphasize why I think this is important. It takes about, as you can see here from the time scale now, it's only 3 different fuels, but you can see that it takes about 30 to 50 years to introduce a new technology until you have production. So if you think that we run out in 2050 of the known resources in fossil fuel, minus the 30 to 50 years, then it's about time to think now what do we do in 30 to 50 years? So this is really what spawned me to look into that. Then, of course, the question is, what is that fuel going to look like? Nobody knows. But if you try to estimate that and you take that together with the climate debate and carbon reduction, carbon emission reductions, the only conclusion there is that hydrogen is going to be more important. Whatever form that is, local transportation, but hydrogen is becoming more important. And so that's when we started looking into fuel cells, how to make that energy. And one thing is also clear, that in order to convert chemical into electrical energy, you have to have a catalyst. And that catalyst, well, as most of us probably know, comes from a very scary part of the periodic table for the calculations, as well as for the simple fact that the abundance of these metals that you would like to use is very rare. And it's inhomogeneously distributed on the globe. So you have to think about that. What materials can you substitute here? And where do you find them? That's sort of the economical geological aspect to that. So what we would like to use in order to look at the environment, energy type applications, well, we would like to have an unbiased method, sort of that allows us to treat everything in the periodic table on the same footing. It's universal, that we don't have to worry about solids versus surfaces versus molecules. It should be predictive, so we can actually give guidance as to what materials we should use. and something that can be improved systematically. And the answer, of course, as we all know, or one answer to that is density functional theory. I've been mainly using VASP 4.6. We're upgrading to 5.2. That's the new version, has exact exchange in it, GW in it, and some other things that also are available, for example, in PWSEF. I've been using that for a little bit. UpInit, Bean2K as an all-electron method. Typical standard fare of things, PAW potentials, some smearing, some relativistic corrections for the heavy elements. And Renata said that I should talk about the computational needs. They are usually between 32 and 128 cores for the structure optimization, so it's fairly small. Then for the transition state calculations, we use that, whatever we have, times the number of images we have for the NEB method, or for the DYMO method, maybe it's something roughly twice as much. But the advantage is these small sizes. If you go to a supercomputing center that has, say, 10,000 cores, you're basically always going to be in the noise. There is no such thing as a wait time for me. I put it in the queue, and it runs almost automatically because it's so small. We're not competing with 5,000 core jobs. It's very small. At least not on the supercomputer centers I run. I have not waited for more than a minute maybe on most of these jobs. So it's very convenient. It's good for students because it's sort of instantaneous response. If they make a mistake, they know right away rather than 5 days later. So educationally, that is something.
Which computer centers you're referring to?
This one, I use TeraGrid, but the waiting time is a little bit longer.
It depends on the TeraGrid resource that
Yes, we're using different ones. We distributed it to benchmark different resources. So we're using, let's see, we're using Ranger, so UT Austin resources. We use Indiana resources, and yes, and then.
There are some resources that don't disfavor small jobs. You can only run several jobs with several.
We looked at that. We looked at that before when we worked for the TeraGrid allocation. We looked at the writing of the proposal. We looked at that was a possibility. The other thing I should say is something we found out the hard way. Is since we use VASP, I looked also what platforms do have VASP available because I thought they optimize it, they install it, and the time it takes to get up and running would be minimized, which is a good idea. It says on the TeraGrid webpage it is available. You actually log into the machines after you get your allocation. It's not there. Then you send email to the helpline or the help desk, and you find out, oh no, we don't support that anymore. So you're on your own, and you probably would have chosen a different set of computers with that if I would have had that advanced knowledge. So there are some things, if you're not comfortable installing software, in other words, it may take you some time, or you need somebody who helps you with the installation. And also, it's not very homogeneous, the set of TeraGrid. Some of them are by module, and there's different mechanisms how to access the things. So if you're not experienced with that, it may be taking a little time, or ask someone to help. That would be a community building aspect, probably, something like that. DOE centers do not have that problem. DOE centers, as far as I know, all have VASP installed. I've not seen a DOE center where VASP, for example, was not installed. You just give them your license agreement, and you're good to go. It takes you literally about 5 minutes after background check. Okay, so flexibility and universality. This is a list of potentials that are available, say, within VASP. Just for fun, the other day I made a list. The brown circles, these are the ones I've been using over the last year or so, and tested, in other words, and the red is what's available. So we have been biased a little bit towards the platinum group elements. But so really, it is universal in the sense that we can treat, at least at some level, every single element. Most of the elements, at least in the periodic table. So I think the universality is good. And that is very important, I think, because it allows us to, at least people like myself, to change from development of codes towards more question-driven research, and that's what I like to do. So a few examples I feel compelled. This is work that we have been doing over the last year. It really is about surface science, engineering, and electrocatalysis. That's at least the goal. So we try to do some defect engineering. Here's the surface of gamma alumina. That's the modeling. And we have aberration-corrected TEM pictures where you actually see these structures here are taken at the limit of your microscopic resolution. And what you see is indeed single atoms, small atom clusters. The problem with that method is that you look straight down. So you don't have any depth perception. You have lateral perception, but no depth perception. And so that's where the calculations come in to help to resolve how many atoms does one of these spots compare to. Is it 1, 2, 3? And you see very faint, probably too faint actually. There's 1 point here, and then sorry, it's too much light here, but there's 2 points. So could it be 2 points, 3 points, 5 points? And then what experimentalists do, they have great experience in evaluating the performance of that, obviously, and the question is, how many atoms do you need in order to get a good catalyst? The reason is, if these elements are very expensive, if they are going to be large, you have lost a lot of the particles that you would like to have towards the interior of the particle, so you would like to spread them out as much as you can, and that's where this question becomes important. The stability, durability, of course, of these materials is very important as well, and that's something we cannot address necessarily directly using these calculations. So defect engineering has become more important. We looked at deactivation, and here's one of these nanoparticles. That's a regular TEM picture. And so the calculations we did diffusion, surface diffusion calculations to find out activation barriers, diffuse some of these aspects. And the curious part about this particular material is that it deactivates within about 2 weeks. So if you want to run a car for a couple of years, then a 2-week lasting application is certainly not what you want. And so the question, can we understand where it comes from and can we avoid it in the future? And the answer is we can understand it and possibly avoid it in the future. And so it turns out that we proposed from the calculations that oxidized niobium forms right at that rim here, goes into a reduced form, and then there's some atomic oxygen. Both of them diffuse on the right time scale along the surface, and therefore our conjecture is that that may be the mechanism by which it deactivates over time, which is then also has been later confirmed by experiments that actually see a reduced rim of NBO2 right around the edges of the nanoparticle where it's under carbon support. Anyway, so these are some of the things we have been doing. There's a few more examples, but I think I skip all that. Non-platinum catalysts will become important, and we go towards biological systems, how to use enzymes for lower power applications, how to extract and add electrons in these systems. So that's tethering stuff. That is large molecules. That's going to be very important. We have been asked by the DOE to write a proposal for that, things like that. But this is really, I think, why we came here, at least in my understanding, and this community development and how to make a computational effort part of Compress. So here's a few thoughts towards the end that I were thinking that may be good. So this is something, when I gave a couple of talks at UT Austin a few years ago, they asked me, where are we going from here? What are we going to do? And so this is simply a laundry list of capabilities that I would like to see partly, and partly what I've been envisioning at the time to work on. So really, there's two things. Transition metals we have been talking about yesterday, strongly correlated systems, for example, I think is a challenge still for DFT, and then very soft matter. So this is really, and then you would like to do all across the periodic table, like 2 benzene molecules, for example. What do they do? A very difficult problem in standard DFT. Even though Don Trula would tell you, with MO6L, you may be able to catch, or it captures the intermediate range of van der Waals interactions as well. But so this is just, maybe a list of things where we can sort of sort ourselves in. What do we need, and what do we envision to do? I think, and then we can compare it to experiment, for example, what we may be able to do. But none of that is easy, obviously. It's all challenging. And so what I call here community coherence. So some of these things are simply reiterating what we talked about what I learned last night. Certainly expert advice, so sort of a hotline. You can call in and you have a problem, and then somebody who has a specialist can help you with that. I don't know exactly how that's going to work. It's a logistical problem, obviously. Maybe there's something more, not as immediate, but you have your regular online dial-in meetings like Skype or Adobe Connect once a month, where you can have an exchange, and you foster an exchange among students, for example, because lots of these problems we don't have to interfere. The students have the knowledge to solve that as a community. And so I think building their confidence that they can work on these problems on their own would be very helpful. Distance education goes along the same way. If everybody teaches 2 lectures on a particular topic in DFT, that will take away from our busy schedules only a little bit of time. It forms a community across the United States, international if you want to, and then we can, of course, have student exchange if you would like to do that in the sense of an REU program, but at the graduate level or the undergraduate level, something like that. So these are some of the ideas, what I call a community coherence. Education and literacy, also important. I mean, of course, we have to provide, get the knowledge, and then online tutorials is, of course, a standard tool. Where does it come from? Somebody has to make it, obviously. Maybe we have teaching materials that we can provide. And I'll come back to that in just a second. And teaching materials, very important, I think.